Now, in the previous video, we examined the objective and the terminology. The next, we are going to introduce the circuit theory. What is this theory? Go a bit in detail. We've got to mention about the theory first. So before coming to circuit theory, we've got to mention the theory, of course. The theory starts with the axioms. Axiom, sometimes it is called postulate as well. What is axiom? Axiom is a proposition which could not be proved mathematically, but assumed as true. So we cannot prove it, but we assume it true. So it seems a bit strange. So we are assuming something true, but we can prove it. We cannot prove it mathematically, but in practice it is true. This proposition, it is explained just underneath sentences. This proposition should be validated by measurements in physical world. So whatever we said as a proposition, we cannot prove it mathematically, but anytime we go to the lab, do what axiom says, after the measurement, whatever axiom says is true. So in the physical world, by measurement, we could prove it. We could say that we could see that it is true, but we cannot prove it mathematically. So it is critical. For example, Euclid plane geometry. One of the axioms is there could be only one parallel to a given line from a node. So if there is a line and if there is a node, there is only one line that we could draw passing through this node, and parallel to the given line is only one. It cannot be two. So that is the axiom in geometry. So this is an axiom in mathematics, but in the physical world, we are going to see now, we are going to say the axiom, and then we are going to validate that axiom in physical world in lab. So what is theorem? Propositions which can be proved mathematically. So these axioms cannot be proved mathematically. The number of axioms is limited. If a few axioms, normally there would be in a theory, not 100, 200 axioms like that. So it is going to be a few of them. And theorem could be many theorems, but these theorems should be proved mathematically by using these postulates or axioms or already been proved theorems. So let's come to our theory now, which is called circuit theory, and the axioms are of circuit theory, Kirchhoff voltage law and Kirchhoff current law. So in practice we call them law, Kirchhoff voltage law, Kirchhoff current law, but in theory we say Kirchhoff voltage axioms, Kirchhoff current axioms. Kirchhoff, let's say law at the moment. Kirchhoff voltage law, we show it in short KVL. Algebraic sum of all the elements voltages within a loop is equal to 0. So we already defined the loop. Loop is composed of the elements. These elements voltages, when you add them up, it becomes equal to 0. It says, this axiom says. We cannot prove it. But if you go to the lab, you could see that that's proved after you measure all the elements, voltages within the same loop. So we've got to pay attention to this algebraic sum. We're going to explain this algebraic sum. Algebraic sum means sign business. Each element voltage must have a sign in front of it. How we're going to determine this sign, we will explain later on. Kirchhoff current law says algebraic sum of all the elements currents connected to a node is equal to 0. So we already said what node is. Now we are saying now all the elements which is connected to a node, these elements, sum of these elements currents equal to 0. So you could write these current equations for each node in the given circuit. What about the voltages? For each loop, we could write a Kirchhoff voltage law equation within the circuit. This says, and notice here, just remind you, there are some information included in this explanation is without elements voltage and current references according to passive sign convention, KVL and KCL equations cannot be written. Algebraic sums means with a proper sign. So if all the voltages and currents must have a proper sign. What is this proper sign? I will explain to you. Let's go into the details of these axioms now. Here are examples. Kirchhoff voltage law equations. So here there is a loop here. And in this loop, we've got 4 elements. So there could be many loops within a circuit, of course, but we are mentioning now one proper example, single one loop. We are going to, for that loop, we are going to write Kirchhoff voltage law equation. Without voltage reference, KVL cannot be written. KVL equations, it should have been said. KVL equations cannot be written. So if you don't put these references here, we cannot write an equation. Because why we cannot write it? Because it says algebraic sum. I am going to put a plus or minus signs in front of these element voltages. I cannot put that sign in without any reference, current or voltage reference of the elements. So we need this. But this is not enough. We also need another reference for the loop. So it says here loop direction. If there is a loop direction and the element current reference is assumed. If we know the current reference, we know the voltage reference, so we could use just one of them because we should choose these references according to passive sign convention that we already know. Just remind you what passive sign convention is. So the current reference should start from plus, voltage plus terminal, and should go to the voltage minus terminal, that arrow. Now how we are going to write it? So we're going to say a rule, but this rule could be changed, but the result would not change. Rule is this: if the loop direction is the same as the element current reference direction, then the sign of this element voltage is going to be plus. For example, C element current reference and this loop direction is from right to left. Right to left, they are the same. So we see element voltage in front of it, we've got plus. Look at B, that loop direction and element direction is opposite. So VB sign is minus. Look at A, loop direction and element A direction is opposite to each other. Then VA voltage sign is negative. And the last one, D, this loop direction and the D element direction is opposite to each other. That's why this is minus D. So that is Kirchhoff voltage law equations for this loop. You could watch this video to see it online. Keeping the voltage references the same, KVL equation is validated for the measurement values. So keeping the voltage references the same, so this reference the same, then you can validate this equation by measuring voltages of these elements according to the given or chosen voltage references. Without determining a loop direction, red shown, this is this one, QVL equations cannot be written. So in the exam or anyway, when you are doing the analysis, before writing these Kirchhoff voltage law equation, you must choose element reference, at least one of them, and also the loop direction. Without this direction, you cannot write this equation. It says, if an element reference and loop direction is the same, then the sign is plus, otherwise it is minus. This is just I said before. This is just an agreement. If the opposite is accepted, then it is also true. So you think about that. Something for you to think about that. The opposite, what I mean by saying opposite, if the loop direction, the element direction is the same, the sign in front of the voltage is going to be minus. When they are opposite direction, the sign should be plus. That is the opposite of that rule. But I am saying if we use this rule, then your result is going to be the same. But you cannot mix those rules up. That means you cannot use this rule for element B and use the other rule for element A. You've got to choose which rule you're going to apply and apply that rule. So the second step is the Kirchhoff current law equations, how we are going to write it. For each node, KCL equation is written. For each node, we're going to write it. Therefore, number of KCL equations is equal to the number of nodes. So how many nodes you have, for each node you're going to write an equation. So the number of Kirchhoff current law equations that you're going to write is going to be the same as the number of nodes within the given circuit. Without elements current references, KCL equations cannot be written. So that means we've got to choose these current references or voltage references if you know the one of the reference, so you can draw the other reference by using the passive sign convention. If the element current references and measurement current references are the same, then the KCL equations are validated. So we are saying, we haven't explained yet, but if you write a Kirchhoff current law equations, then you can validate this after, if you do the measurement of these element currents according to that reference, then it is validated. That's why we need these references. If let me come back now again. Something happened, don't worry. If an element current reference is out of the node, then this element current sign is plus, otherwise towards the node its sign is minus. So when they say algebraic sum, the Kirchhoff current law equation says that for each node, all the elements connected to a node, these elements current summation is equal to 0, but it says algebraic summation. That means there's going to be plus or minus sign in front of each current. How we are going to determine this plus and minus sign in front of a current? We've got to make a rule saying that if an element current is out of the node, for example, that D out of the node, and A element current is also out of the node, the sign of these elements are going to be plus, A and D plus. If the element currents towards the node, then the current sign is going to be negative, 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 negative. So you could write the opposite rule for this, but I am saying the opposite rule ends up with the same equation. So you could think about it and try to prove what I said is true or not. So you could see step by step how these currents are going to be written by watching this video. Let's come one more thing. Conclusion, what was said about the circuit theory. Let me to read them. It will be appropriate to choose randomly a current reference for each element. So in the previous one here, we have chosen element voltage and current references together. But since we are using the passive sign convention, we do not draw two of these references, just one of them enough, it says. So in here, we have chosen a current reference only. So it says, in general, this current references is chosen. No need to choose voltage reference since it is determined according to passive sign convention. While writing Kirchhoff voltage law, it is needed to choose loop direction reference, red one. We've got to choose this, otherwise you cannot write it. While writing Kirchhoff current law, an element current, so we've got to mention the rule that we just said. Anyway, it was a bit, it's not complete now. Let me finish this first. Once you choose the loop direction, you can make a rule writing the proper sign in front of the element voltages. That rule is the element current signs and the loop direction is the same direction. Then the sign in front of these element voltage is going to be plus, otherwise minus. The rule for the Kirchhoff current law equation is this. Those elements current reference towards the node is going to have a minus sign in front of their current. If it is opposite, the plus sign is going to be in front of these elements currents. So that is the end of it. So what we have done, we said our aim is circuit theory, we explained the terminology. On the base of this terminology, we explained what these circuit theory axioms are. Kirchhoff voltage law and Kirchhoff current law. By using the axioms, we are going to conduct a mathematical model. That's the next video that we are going to see or observe.